Have you ever wondered how your computer manages to do multiple tasks at once? The answer lies in the magic of multi-threaded programming. Imagine a thread as a basic unit of CPU utilization. It's made up of a thread ID, a program counter, a register set, and a stack. Threads belonging to the same process share the code section and data section. Output. In a traditional or heavyweight process, there's only a single thread of control. However, if a process has multiple threads of control, it can perform more than one task at a time, making it a multi-threaded process. Why is multi-threaded programming so important? The reason is simple. The software packages that run on your modern PCs are multi-threaded. An application, like a word processor, might have one thread for displaying graphics, another for responding to keystrokes, and a third for performing grammar checking. In some cases, a single application might need to perform several similar tasks. A web server, for instance, might create a separate thread for each client request, allowing it to service several concurrent requests. Most operating system kernels are also multi-threaded with separate threads, managing different tasks like device management or interrupt handling. Multi-threaded programming offers numerous benefits. It increases responsiveness as a program can continue running even if part of it is blocked. Threads share the memory and resources of the process to which they belong, facilitating resource sharing. It's also more economical to create and context-switch threads than to allocate memory and resources for process creation. Lastly, in a multiprocessor architecture, threads can run in parallel on different processors, increasing parallelism. So, how are threads provided? They can be provided either at the user level for user threads or by the kernel for kernel threads. User threads are managed without kernel support, while kernel threads are managed directly by the operating system. There are three ways of establishing a relationship between user threads and kernel threads: the many-to-one model, the one-to-one model, and the many-to-many model. In the many-to-one model, many user-level threads map to one kernel thread. This model is efficient as the thread management is done by the thread library in user space, but it has its drawbacks. If a thread makes a blocking system call, the entire process will block, and multiple threads cannot run in parallel on multiprocessors. The one-to-one model maps each user thread to a kernel thread. This model provides more concurrency and allows multiple threads to run in parallel on multiprocessors. However, creating a user thread requires creating the corresponding kernel thread. Lastly, in the many-to-many model, many user-level threads are multiplexed to a smaller number of kernel threads. This model allows developers to create as many user threads as necessary, and the kernel threads can run in parallel on a multiprocessor. In a nutshell, multi-threaded programming allows your computer to perform multiple tasks simultaneously, increasing efficiency and responsiveness. It's the secret sauce that makes today's software applications so powerful and versatile. Remember, threads are the magic behind how your computer does more than one thing at a time.